Alright guys, we're going to get into section 2, which is now going to focus more on probability, statistics. Statistics and probability really go hand in hand because statistics is always used for probability purposes. Obviously used to make predictions and estimates and all that kinds of stuff based on the statistics. So, what we're going to be looking at on this one, and probably at one point or another, almost all of you will end up taking a statistics course. So many students oftentimes go into AP Stats their senior year. Good chance you'll have to take it in college. I had to take it in college, so this will lay a good foundation for some stats, and you'll definitely recognize some of this stuff. I guarantee you, some of these things come up as early as pre-algebra. So I think you guys will recognize quite a few things in here. So we're going to talk about just sort of some really few different types of data and how to describe it, and then the focus is going to be on the different types of diagrams. They're going to come into play with these guys. So let me keep it moving. All right. So it starts out with just a super basic idea of, if I were to gather some data, let's look for some kind of a relationship, right? And so we're just looking for some kind of a connection between the data. As I look at these, so they were talking about males and females and different types of sports that they like to attend live. Okay, and so some obvious differences in here, but as I look at the numbers, it's a little tough to compare males and females because it was a different sample space, right? It wasn't the same amount. And so it's a little hard to compare some of the numbers from one to the other if the totals were different. And so they suggest, well, one of the things you could do is convert all these to percentages, and then they would be easier to compare. And so they said, well, let's just change all these to percent. So if you did like 31 out of 398, and then 54 out of 398, and then you did all the same thing for the females out of 447, and if you change them to percentages, then it's much easier to compare the data. Okay, and so that's just kind of the first part, is just let's change everything to percentages, because percents are always out of 100. So that puts them onto more of an equal playing field, and now I can make some easy comparisons, right? Like according to this, way higher percent of females would attend basketball live, way higher percent of males would attend football live. Pretty darn close when it comes to hockey, things like that. But you can now sort of make all those observations much easier if you look at these guys more on common terms. So for this one, we are now looking at comparison of two different types of data, just like really like what they did on the other one, and they're talking about, males, females, and in this case, it's about what level of education they teach. So these are teachers, and so they put them into one of these types of observed data charts. And so from this, we're now going to get these expected frequencies from this data. So they want to get these percentages, but they want to make it relevant to both items that are being compared. So if we were looking at, say, the percentages that we would expect for males in higher education, so just based on these numbers, so it's got to be a male, so there's 80 of those. Got to be in higher education, there's 34 of those, out of these 200 teachers. So here's the formula. So it's the row total, so total number of males times the column total, which was the total number of teachers in higher education, and then they divide that by the total sample size, which was 200. Right? They use that to come up with what they call an expected frequency of 13.6. In other words, if you have 200 teachers, they would expect 13.6 of those teachers to be males in higher education. So then they went on to do this for secondary, primary, and they did it for all 6 cases. Let's just maybe try it for a couple of these, but again, let me show you where this one came from. So if we were talking about males in secondary education, then again, you would take the total number of males, which is 80, times total of secondary education, which is 94, divide that by 200, and that's where you get the 37.6. right? And so again, it's all based on the sample size. So it's out of these 200. So if you had actually 200 teachers in a group, they would estimate that 37.6 teachers would be males in secondary education. All right, let's just try it for one of these guys. So let's look at females in higher education. So if I had a group of 200 teachers, how many of those 200 would I expect to be females teaching higher education? So we take, again, this is just going into this basic formula. So for females, we got 120 times 34, because this is higher education, and then divided by 200. So let's see what we got here. So if I did 120 times 34 divided by 200, we're looking at 20.4 as our expected frequency. All right, so we're not going to fill out the whole table. Obviously, that's something you guys can do. You'll see that come up in the homework. I just wanted to make sure you guys saw where that's coming from and give you that little formula that they're using for that. All right. So as you know, statistics likes to really throw out some cheerful statistics out there. So the leading cause of death in the United States in 2010, and they come up with our list of death over here. So, numbers of deaths, and then they got broken those down into percentages. So let me take you to the next page where they're using that information. So one of the things I wanted to show you guys on this is just some of the different types of graphs that they're going to use. And what kind of one of the important things to note on this is, how do you know which graph is best to use for which cases? Because that's one of the things that you're going to be asked. So as you look at this bar chart, obviously you got your categories down here at the bottom, you got your numbers on the y-axis as kind of our frequencies, and so that's the way this guy is broken up. And so with the bar chart, one of the things they'll tell you is bar chart's good when things are in categories, like heart disease, cancer, whatever, right? So notice in a bar chart, these are not numbers, they're categories, right? When we were going to do another one here in just a second called a histogram, and the big difference between the histogram is a histogram, these are numbers, not categories. And so that's one of those little differences that you kind of need to take note of on this. Obviously, the graph is very simple, right? It simply goes as high as whatever its frequency is. So a big part of this will just be kind of just note when these are good to be used. So for the circle graph, again, kind of a category thing, right? You might call this a pie chart, same thing, right? But again, it's categories broken up into percentages. All right, let me take you to a stem plot, also known as a stem and leaf plot. You might have seen one of these before. So if I have all this data, this one was just percentages of residents that were 65 or older. And so as you look at all these, so these are percentages. So like in Alaska or Alabama, whatever that is, 13.8% of their population is 65 or older. So obviously with a big chart like this, there's obviously a whole lot of numbers. It can be tough to compare data in something like this. And so they want to use something like a stem plot in order to make it easier to visually see the comparisons and make some observations about the data. And so that's really the point between any graph, is to make it more obvious as to certain things that might stand out to you. So here's how the stem and leaf plot or stem plot would work. Right, it gets organized to something like this. Okay, and so as you look at those same percentages, so this would have been 7.7%. You can see that there was none in the 8% category. This one was 9.0%. When you see the multiple numbers, so this would have been 10.3%, 10.7%, and 10.9%, 11.4%, on and on and on. Right? So now, but by organizing it into the stem and leaf plot, you can now see some things that would stand out to you, like the majority is in the, or the mode, I should say, is in that 13% range, right? Somewhere in there. And so obviously the heart of the data is, you might say, in the 12 to 14% range. That's where, most of the percentages of 65 and older would go. But obviously those numbers stand out to you so much more clear now that it's organized into a stem and leaf plot. These can be anything. They don't have to work in tens. It's sort of up to the person making the stem and leaf plot on how they want to organize the numbers. So let me show you a different scenario with one of these. So on this one, they're now talking about some home run statistics from some old ball players. So you got Babe Ruth, Barry Bonds. You guys probably know who those are, I'm sure. And just comparing some of their numbers for home runs. So one of the other things you can do with this, if you want to compare two different sets of data, would be something called a back-to-back stem plot. So if you look at some of Babe Ruth's numbers that you see over here, obviously these are all like in terms of tens. And so that's how they organized sort of the main branch of this stem plot. So if you look at the way they did this, so here's what we would see for this. So obviously everything after the zeros are just taken at face value of numbers under 10, right? So 1, 3, 3, 6, or Barry Bonds had 5 in that year. The next one down is, so now you're getting into the tens, right? So this would be like 11. That would be 16 and 19, right? Over here you're looking at 22, 25, 29, on and on. Okay, so we're just using the stem as a way of sort of organizing the numbers, putting them in order, and now looking at what stands out to us. Obviously, they were both had more in the 40s than anything else. But again, just one of those comparisons that's a little easier to tell if you organize the data into a graph like that. All right, histogram. You guys probably seen a histogram before. Couple things that are different about the histogram, because it looks a lot like a bar chart or a bar graph that we saw earlier, but it talks a little bit about in here sort of the differences on this. So remember, this is about having a numerical scale on both axes, and so these now represent numbers down here, not categories. So that's one of the biggies. The other one is when you do a histogram, one of the rules that they try to stick with is there's not supposed to be any gaps between the bars. Right? These are supposed to be connected the way that you see them on here. If you do see a gap, it's because that simply represents an area of the graph where there was a zero frequency. So we're going to practice making a histogram off of this data right here. So here is a frequency table. So as you look at this, back to the home run conversation, so this was Mark McGwire annual home run totals within those years. So as far as getting 0 to 9 home runs, that happened 3 of those years. From 10 to 19 home runs, that never happened in any of those years. From 20 to 29, so some home runs in the 20s, that happened twice. Home runs in the 30s, that happened 5 times. In the 40s, 50s, 60s. And so we have this frequency table, and so we're going to use that to make a histogram with. I'm going to show you how to do this by hand and with some technology. So let me set this one aside for a minute. Here's one thing I want to point out though on this is how do we do it so that we don't have gaps when there's naturally a gap between the numbers. If my first bar is supposed to go from 0 to 9 and my second bar is supposed to go from 10 to 19, well then naturally there's going to be a gap between 9 and 10, right? There would be a space there. And so what they do to avoid that is instead of making this bar's width go from 0 to 19, they widen it out to the middle of what would be between him and the next number. Okay, so, and then that's where this next one will pick up. So instead of going from 0 to 9 and 10 to 19, they're going to make this one go to 9.5, and then this can go from 9.5 to 19.5. And then this can go from 19.5 to 29.5. This one goes from 29.5 to 39.5. So by hitting those numbers in the middle with the two widths, that's where the bars will connect and then no longer have any gaps between them. Okay, so that's when we draw our own histogram here. That's the way that we're going to do this. So let's throw out our y-axis. And here's our x-axis. Always good to label these. So this was always our frequency, or you could, and this guy's going to be our number of home runs. All right, so good to know what those things represent. So again, they're going to do the first one from 0 to 9.5. And actually, you could even take this from negative 0.5 to 9.5. That way, they all have the same width of 10 units, which would be a good thing to have. So I'm going to make a mark for 9.5. And then we're going to make one for 19.5. So let's see, that's going to be 19.5, 29.5, 39, 49, 59, 69, 79. Okay, so 9.5, let me just label those real quick. All right, so there's our home run groups. And as you look at the frequencies, realistically, as I look at those frequencies, the lowest number is 0, the highest number is 5, so I would just count by ones in a case like this. So we're going to say 1, 2, 3, 4, 5. All right, represent our frequency list, and so now we're just going to throw in the drawings for this. So from 0 to 9, there was a total of 3 home runs. So again, they're going to, instead of ending it at 9, they're going to end it at 9.5 for 3 home runs. And again, they're doing that so that it will now connect to the next bar. So if this one ends at 9.5, this one begins at 9.5. So this one is now going to go from 9.5 to 19.5. And there was 0 in there, so we're just going to leave that guy empty, because that one had a 0, and then I'll just kind of go through and quickly fill in the rest of these. So then for the next one, that would go, so if that one ended at 19.5, this one begins at 19.5 and goes to 29.5 with a total of 2. So from 19.5 to 29.5, as high as 2. Next guy goes as high as 5. Then we had 2, 2, 1, 1. And there we go. So there's our histogram. Now that it's been graphed, now we could point out some of the things that might stand out to us, right? Like the mode was the 29.5 to 39.5 range. That was his most likely to hit within the 30s. That happened 5 different times. So things like that that you can now point out by seeing that. So let me show you how to do this on Desmos, where you can make a histogram. A couple things. Let me mention this first. When it comes to the graphing calculators, doing graphs like this, like statistical graphs, is really more trouble than it's worth. You can do it on here, and it will give you this image. But it's a pain, and it's kind of a pain to remember all of the different settings that you have to create and everything else. And to be honest, it's just not worth it, because it's so easy to make a histogram, right? There's nothing complicated about making that graph. It's so easy. So really you don't need technology to do graphs like this. So we're really not going to be using stats tools for graphs like this, because even if you did use one, what would you do with it? I mean, if you had to make a histogram by hand, you'd still have to draw it out by hand, even if you used a stats tool. So there's really not much gain from that. So we're not gonna be using stats tools for these types of diagrams. It's just too simple to do these things by hand. So let me go down to these guys. So 2 descriptions I want you guys to be familiar with on this. There's 2 different ways to describe this. One has to do with how many modes you see. So a mode is think of the word most. So it's like, what do we have the most of? And so with these guys, they try to describe these as like how many clusters they have. So they would call this unimodal. So unimodal, it's right down here. Because there's like one big cluster where the data is obviously centered around this area right here. If that has 2 different clusters like this one does, like 2 different main groups, they would call this bimodal. So you'd be familiar with those, whether it's unimodal or bimodal. And then as far as it being skewed to the left or to the right, or whether it's symmetric. This one is symmetric because it's obviously centered in the middle of the graph. However, let me show you this. These are ones that are not symmetric because they're not centered in the middle. So, or the main cluster is not in the middle of the graph. If the main cluster is, let me make sure you can see all this. If the main cluster is to the left, they would call this right skewed. When I first read that, I thought, why would they call it right skewed when the cluster is to the left? Well, they don't base it on the cluster, they base it on what they call the tail. So if this is like the cluster, and then you can see it kind of tails off to the right, so that's why they would call it right skewed. And then this guy, so if over here is the cluster on the right side, and then it tails off to the left, so they call this one left skewed. So be familiar with those as well. That's something you guys will be asked about. All right, so a little bit of description on those we got to be familiar with. There we go. And then let me take you down to this one. So the last one we're going to talk about is called a time plot. Super simple. It's basically plotting coordinate points, right? X, Y points where they always put time on the x-axis, so that's something to note. And then they put the data on the y-axis. And so that's something we always want to stick with when we're doing this. It is going to always be things that are measured, like values. So that's why these ones are not very, a time plot is something you would use if it's all like number based over time, not categories, like the first ones that we talked about. So line graph, also called a time plot. Let me show you one. So here's a pretty detailed one of a time plot, so things that occurred over time. This one had to do with like interest rates. And so you can see like as interest rates went up and down over time, it's like this continuous data where they just plotted points and connect the dots. If we had one that was a little more rigid, a little more of a connect the dots here. So this was just another case where they used, again, they're using time as the x-axis, and they were using the y-axis as, in this case, it was dollars. So here's the data table at the top. Sorry, let me show you this. This was credit card debt in billions. Credit card debt in billions. And so from 2004 all the way to 2012, so it started out with 707 billion. Over here we're looking at 661 billion. You can see there was a peak right here in the middle. But again, they're plotting these over time so that things will stand out to you, like how it grew or decreased or whatever. Okay, so but otherwise it's really pretty simple graphs, just plotting them. You could use this, and this would probably be a good use for these as well, maybe even better, is if you were going to compare two different time plots, right? And so this is now the one where they're comparing student loan debt to credit card debt, if you look down here at the bottom. So they're talking about comparing two. It's like literally as simple as putting two plots on the same graph, right? So just plotting points. And then obviously we could make a comparison on this. You can see as one continued to increase, the other one started decreasing over time. However we wanted to describe it based on that, right? But that's the idea of a time plot. And that's going to be it for section 2.